Bismillah ar-Rahman ar-Rahim. Our today's lecture is related to the polynomial splines, chapter 5. And as we said in the previous chapter regarding interpolation, if we have large number of data points, say 10 data points, and we want to construct a single interpolating polynomial to connect those data points, then the polynomial order will be of order 9. And this will have several problems if we will construct a single polynomial for large number of data points relatively. The first disadvantage is that a lot of computations are required. The second disadvantage is about round-off errors. And the third disadvantage, as we discussed in the last example of the previous chapter, is the oscillation near the edges. So there will be high oscillations near the edge points from the lower side and the upper side. And this is why we use interpolating polynomials for relatively low number of data points, like say 3, 4, 5 data points. But if we have like say 10, 50, 100, we don't use interpolating polynomial, single interpolating polynomial. And this is the main motivation for the polynomial splines. So in this chapter, we will discuss it under a very general umbrella. We will discuss the polynomial splines under a very general umbrella. Okay, and here we will consider that we still have n plus 1 data points ranging from x naught f of x naught till xn f of xn. And what we are interested in, we are interested in constructing n polynomials. And each polynomial should be of certain order, degree m. The polynomial order will be of order m. And each polynomial will connect only two successive data points or pair of data points that are successive to each other. For example, if I have the ith polynomial, it will connect xi minus 1 with xi. So, in order to clarify things more, let me check okay, this point. Assume that we have here x naught, x1, x2, x3 until we reach xn minus 1 and xn. So we assume that this is x naught, this is x1, this is x2, this is x3, and this is xn minus 1, and this is xn. Okay. So these are pair. What I mean that x naught f of x naught, x1 f of x1, x2 and f of x2, x3 and f of x3. They are pair of data points, the x value and its corresponding f value. Okay. So using polynomial splines, we will connect x naught and x1 with a polynomial. x1 and x2 with another polynomial. This is random polynomial. Okay, this is random polynomial. Then x2 and x3 with another polynomial. And we continue in this process till we reach to the last polynomial, which connect xn minus 1 with xn. So we give the first polynomial the simple f1, the another one f2, the third one f3, and this final one will be Fn. So, how many polynomials do we have? We have 1, 2, 3 till nth polynomial. So we have n polynomials connecting n plus 1 data points. So if we have n plus 1 data points, so we will construct n polynomials. Okay? And in order to remember the index of the polynomial, okay, will be equal to the right hand side point. We said that each polynomial connect two data points. So f1 connect x0 and x1. Okay. f2 connect x1 with x2. f3 connect x2 and x3. And finally fn connects xn and xn minus 1. And as I mentioned previously, when I mean x, I mean x and f, x and f. So x0 and f of x0, x1 f of x1, x2 and f of x2, x3 and f of x3, xn minus 1 and f of xn minus 1, and xn and f of xn. So if we want to remember the rule, we should pay attention that the subscript for the polynomial is equal to the index of the right data point. So f1, this is our right. f2 is equal to the index, this index. f3 is equal to this index. fn is equal to the index of the right hand side data point. So again, as I mentioned, we have from f1 till fn polynomials. So their number, they are n polynomials. They are n polynomials connecting n plus 1 data points. N polynomials connecting n plus 1 data points. And each polynomial connect a pair of successive data points. So f1 connect this f1 connect x0 with x1, f2 connect x1 with x2, f3 connect x2 with x3, and finally till we reach to fn that connect xn minus 1 with xn. So each polynomial connect a pair of successive data points. So we assume that we have n polynomial connecting n plus 1 data points, and the order of each polynomial, if we assume that fi of x, the ith polynomial, it's of order m. So it will be a0 plus a1 x plus a2 x squared plus till we reach am xm. Okay? So here each polynomial of the n polynomials, we have n polynomials. Each polynomial, we give it the general description fi of x, which might be f1, f2 till fn. It consists of mth order polynomial. The order of this polynomial is mth order. So this is the order of the polynomial, m. And all of you know that for an mth order polynomial, the number of unknown coefficients a0, a1, a2 till am will be m plus 1 unknowns or coefficients. The number of coefficients for an mth order polynomial, this polynomial is an mth order polynomial, this polynomial. And it contains the coefficients from a0 till am. So what's the number of unknown coefficients? They are m plus 1. So we have n polynomials, and each one of them has m plus 1 unknowns. So what are the total number of unknowns that we are dealing with? The total number of unknowns will be n, which is the number of polynomials multiplied by m plus 1, which are the number of unknown coefficients in each polynomial. So this is the total number of unknowns on all of the splines, in all of the polynomials. We have n polynomials from f1 till fn, and each polynomial has m plus 1 data points from a0 till am. So what's the total number of unknowns in all of the polynomials from f1 till fn? They will be n multiplied by m plus 1. So this is what we are interested in. This is what we are speaking about. So let us go back to the original chapter. As I mentioned, the ith polynomial connect xi minus 1 with xi. For example, we have the first polynomial, the second, third, till the nth polynomial. So we have, according to equation 5.1, n polynomials. Each of those polynomial, it's mth order. It's mth order. The first polynomial, f1, connects x0 with x1. The second polynomial connect x1 with x2. The third polynomial connect x2 with x3. And finally, we will reach to the nth order polynomial that connect xn minus 1 with xn. So, in those polynomials, their number is n polynomials. And each polynomial is of mth order. And as a result, the number of unknown coefficients is n multiplied by m plus 1. Those are the unknown coefficients in all of those coefficients in equation 5.1. So I think, and I wish that everything is clear regarding the polynomial construction that I have discussed in previously. So the number of unknown coefficients is n multiplied by m plus 1. We want to solve those unknown coefficients. How can we solve? We should get a similar number of conditions or constraints or equations. In order to solve those n multiplied by m plus 1 unknown coefficients, okay, we should generate a number of conditions, which is a number of constraints, which is the number of equations of similar number, that is n multiplied by m plus 1. There should be n multiplied by m plus 1 conditions or equations in order to solve the unknowns. So how can we generate those? How can we generate those equations or those conditions or those constraints? Okay. Assume that we have 3 points, I minus 1, I plus 1. This is xi minus 1 with fi, f of xi minus 1. Okay, this is xi and f of xi, and the final one is xi plus 1 and fi plus 1. So this is the final data point. So we have three data points, okay, in the general case. And we want to construct the first polynomial between xi minus 1 and xi, and another polynomial between xi and xi plus 1. So this polynomial is fi, and this polynomial is fi plus 1. Don't forget that this index is equal to the index of the right hand side point, and this index is equal to the index of the right hand side point. So how can we generate the conditions? Okay, if the first condition, if we want to find fi at xi, this means that what's the value of the ith polynomial at xi, which is the left node, this one. It should be from the data points, which is f of xi, which is this one, fi minus 1. Okay, and the second is the right point. The second is this point. What's the value of fi at this point? It is fi at the right node xi plus 1 is equal to f of, sorry, the first one is xi minus 1. The first one is xi minus 1. So in the first case, we find the value of fi at this node xi minus 1. So fi at xi minus 1 is equal to f of xi minus 1, which is the given node, given data point. And the right one, this right one, okay, fi of xi, not plus 1, fi of xi, okay, is equal to f of xi, is equal to f of xi. So we have this polynomial passing through xi minus 1 and xi. So its value at this node is f of xi minus 1, and its value at this node is f of xi, or fi. So from this, what's the index of the I? It will be from the first polynomial till the nth polynomial. So how many conditions did we generate? From the first set of equations, this, we will generate n conditions. And from the other equation here, we will generate n conditions. So we will generate n conditions from the first equation and n conditions from the second, and their total, they will be 2n conditions. There will be 2n conditions. Okay, so the total number of positional conditions regarding the left node and the right node for all of the polynomials is equal to 2n. And this is logical because we have n polynomials, and each polynomial passes through a data point from the left and passes through a data point from the right. So there will be for each polynomial 2 equations, and their number is n. So this means that we will get 2n positional conditions that the following, the concerned or the relative polynomial is passing through 2 data points, one from the left and one from the right. So in the first case, we will get 2n conditions regarding the position condition. So if we go back to our conditions, with that we will generate. So this is what I mentioned. Fi at the node xi minus 1, it will be f of xi, and this is for all of the polynomials, so we'll generate n conditions. And fi at the right node xi is equal to f of xi, and this is generated for all i's from 1 to n, and this means that we have generated 2n conditions according to equation 5.2 and 5.3. If we add n plus n, there will be 2n. Okay, now we will switch to the another set of conditions. Another set of conditions. Okay, again, assume this is xi, this is xi plus 1, sorry, this is xi minus 1, this is xi, and this is xi plus 1. Okay, and we have, this is the first polynomial and this is the second polynomial. This polynomial, we called this polynomial fi, and this polynomial, we call this polynomial fi plus 1, which is equal to the index of the right node. Okay, so we have generated two unconditions from the left and right equalities for each polynomial that should pass through the left node and the right node. So what are additional conditions that we might generate? The additional conditions that we might generate is related to the continuity. Is related to the continuity condition at all of the interior nodes. All of the interior nodes. That if we take the ith polynomial and we take this interior node xi and we want to calculate its kth derivative. So we want to calculate the derivative of this polynomial at this node xi, which is the interior node, or via points we call it. Okay, it should be equal to the derivative of this polynomial at the same node. So it should be equal to the kth derivative of the right one, fi plus 1, at xi. So this is what we mean, that assume the first derivative of this polynomial at this node should be equal to the first derivative of this polynomial of I plus 1 at this node. The second derivative of this polynomial at this node should be equal to the second derivative at this node. Also, the third derivative of this one, okay, should be equal to the third derivative at this node. So we take a number of derivatives corresponding to kth derivative, okay, for the left polynomial fi and for the right polynomial at the interior node, which is xi. Xi is surrounded by fi from the left, polynomial fi from the left, and polynomial fi plus 1 from the right. So both polynomials at this xi, they should have equal derivatives. Okay, and what about the k, index for k, the range of k? So it should have equal derivatives from k equal to 1, okay, which is the first derivative, till k is equal to m minus 1. M minus 1, which is the order of the polynomial minus 1. So this k is within the range between first derivative and m minus 1 derivative. So it's within this range, this k. So we take, assume that we have a fifth order polynomial for all of the splines. So we take the first derivative from the left should be equal to the first derivative from the right for the right polynomial, and the second derivative for the left polynomial should be equal to the second derivative for the right. The third derivative of the left polynomial should be equal to the third derivative of the right polynomial, and the fourth derivative of the left polynomial should be equal to the right polynomial, to the fourth derivative of the right polynomial. All of them, they should be calculated at xi, and xi is any interior node or any via points that's surrounded by left polynomial spline and right spline. So if we want to think about what is the index of I here, the index of I that correspond to all via points, if we remember the range of data points, they are from x0 till xn. So x0 does not have any polynomial to its left, and xn does not have any polynomial to its right. So x naught is not an interior node and xn is not an interior node. They are edge nodes. So what are the rest of nodes that are interior nodes? They are from x1 till xn minus 1. So the I in the previous description is limited for the interior nodes, which is the range between 1 and n minus 1. Between 1 and n minus 1. This xi and this I that I have described, this I, which is the interior node index, okay, that we calculate the left and right derivative should be equal. It's confined for the range between 1 and n minus 1. X naught does not have any polynomial to its left, and xn does not have any polynomial to its right. So what are the nodes that have polynomials to their left and polynomial to their right? They are from x1 till xn minus 1. So the I index is between 1 and n minus 1. So to summarize, I is within the range of 1 till n minus 1. And k, the derivative order, was within the range from the first derivative till the m minus 1 derivative. So what are the total number of continuity condition on the derivative? We call those conditions continuity conditions of the derivatives, which are those, as I have mentioned here. Those are the continuity conditions. Those are here. The kth derivative for the ith polynomial at xi should be equal to the kth derivative of the I plus 1 polynomial at the same node xi. So I is within the range between 1 and n minus 1, while k is between 1 and m minus 1. So how many conditions we can generate from this continuity condition? So I, as I mentioned, I is within the range 1 to n minus 1, and k, the derivative, is between 1 and n minus 1, while I is the number of interior nodes, which is between 1 and n minus 1. So finally we will generate n minus 1 multiplied by m minus 1 conditions from those derivative continuity condition, and this is what is written in this page. So here, this is the third condition. The kth derivative for the ith polynomial at xi should be equal to the kth derivative of the I plus 1 polynomial at xi, and k is between 1 till m minus 1, and I between 1 and n minus 1. So we'll generate n minus 1 multiplied by m minus 1 conditions. Okay? So what are the total number of conditions from the above three conditions as given on those equations? So it will be n from the first, n from the second, and n minus 1 multiplied by m minus 1 from the third. If we sum all of those, we will get this: n multiplied by m plus 1 minus m minus 1. So don't forget that the total number of unknowns, as we mentioned before above, is n multiplied by m plus 1. And the total number of equations or conditions or constraints is equal to n multiplied m plus 1 minus m minus 1. So if we want to write again, the number of unknowns is equal to n, the number of polynomials, multiplied by m plus 1, which is the order of the polynomial, plus 1, which is the number of unknown variables a naught from am till am in each polynomial. So the number of unknowns is n multiplied by m plus 1, and the number of equations or conditions is equal to n multiplied m plus 1, as we take in the previous page, minus m minus 1. So, is there any similarity between the two cases? So, this here and this here, they are identical. So, the number of equations is less than the number of unknowns by a factor of m minus 1. So, in order to solve this system of linear equations uniquely, we should have the number of unknowns equals the same as the number of equations. So, the number of equations in the current condition, in the current situation, is less than the number of unknowns by a factor of m minus 1. So, we have a deficiency in the number of equations. We have less number of equations than the number of unknowns by m minus 1. What we can do? So, we should add m minus 1 additional conditions to the system such that the number of equations will be identical to the number of unknowns, and we should add those n minus 1 conditions. We should add it to the system. So what and where we will add those conditions, we will see on the same page. So here it's written that the total number of conditions is less than the total number of unknowns by m minus 1. And in order to solve the system uniquely, m minus 1 conditions, additional conditions, should be assumed in order to make the number of equations and the number of unknowns the same. So, these additional conditions, which is m minus 1 conditions, they are added generally on the initial node and the final node. What we mean? x naught and xn, regarding their derivative values. So, regarding like the first derivative, second derivative, okay, this is generally the first derivative and or the second derivative. Okay, so m minus 1 conditions will be added on the initial and final node. So, in order to have symmetrical conditions, in order to have identical and symmetrical condition on both nodes, x naught and xn, so this m minus 1 conditions, they should be even number. How? So we have m minus 1 additional conditions, and those m minus 1, they should be distributed for x naught and xn regarding the derivative values of their functions. Okay, so we have here two nodes, x naught and xn. So in order to distribute, like assume that I have said that f prime of x naught is equal to 0 and f prime, the first derivative at xn, also is equal to 0. So this means that we should have two conditions. If I add the second derivative also, there will be 4. So this means that in order to distribute the number of conditions equally between xn and x naught, the number of additional conditions should be even in order to distribute them within x naught and xn. If they are odd, one of them will be higher in the number of conditions than the other by 1. So this means that m minus 1, in order to distribute the conditions equally between x naught and xn, it should be even. So what does this mean? We should not forget that m is the order of the polynomial. So if m minus 1 is even, so what will be m, which is the order of the polynomial? It should be odd. Okay, so we should have like the order of the polynomial might be 3, 5, 7. If the order of the polynomial is odd, then the additional conditions are even and we are distributing those conditions equally, the same number between x0 and xn. But if the polynomial order is even, then m minus 1 will be odd. And if m minus 1 will be odd, one of the nodes, x0 or xn, will have one more condition than the other. And we prefer to have symmetrical conditions distributed among x0 and xn, and this is why we prefer using third, fifth, or seventh order polynomial spline orders instead of second, fourth, and sixth order splines, because in the odd case of the splines, the additional conditions, those m-1 conditions that we add, they are distributed equally between x0 and xn. While if the polynomial order is even 2, 4, 6, then we might distribute it not equally, assume that it was 4. So it was 5, sorry, the additional conditions, m-1 was equal to 5, and the polynomial order was 6. Polynomial order m was 6, so m-1 will be 5. And this 5, we might distribute them as 3xn, 2x0, or 3x0 condition and 2xn conditions. So they are not equal. One of them will be higher than the other by 1, and this is the major reason behind the fact that if we return back to all of the books, they generally use third order splines or fifth order splines. They generally use third order splines which are cubic, or fifth order splines instead of second or fourth, instead of fourth and second. Why? Because if the order of the spline is odd, the additional conditions are even and they are equally distributed between x0 and xn. So I wish by this clarification everything is clear. Okay, now we will continue our discussion. So here we have the total number of unknown. The total number of unknown conditions is n multiplied by m plus 1. Total number of conditions after the addition of m minus 1 conditions, they are the same, n multiplied by m plus 1. Total number of position conditions at the initial and final node for each polynomial spline is 2n. And total number of derivative continuity conditions is equal to m minus 1 multiplied by n minus 1. And those conditions which we add in order to have the number of equations equal to the number of unknowns is m minus 1. Okay, so regarding this point or this paragraphs, it's not required from you. Okay, and we will continue this chapter with this table. This table summarizes the previous fact that we have here the spline order, the polynomial order, first, second, third, fifth. Okay, and based on the equation, total number of unknowns will be n multiplied by m plus 1, and this is for each case we calculate the total number of conditions. The total number of position conditions, it's constant, 2n. And the total number of derivative continuity conditions, it's like here for the second n minus 1, for the third polynomial 2n minus 1, and for the fifth order polynomial it's 4n minus 1. And here the number of additional conditions which are m minus 1. In the first order we don't have any, there's no need. And in the second order splines we have 1. In the third order spline we have 2, and in the fifth order spline we have 5. So what are the nature of those initial and final conditions that we add? In the first order spline there is no, because here 0. In the second order spline we have 1. So it's written here any one that we can add only one condition of the following 4 conditions. The second derivative equals 0 at x0, the second derivative at xn is equal to 0, or the first derivative at x0 is equal to 0, or the first derivative at xn is equal to 0. So we can add any one of those. But in the case of third order spline, we add 2 conditions. So here it's written any of the following 3 pairs. This means that we can add 2 conditions simultaneously. So what are the pair of conditions? The second derivative at x naught is equal to the second derivative at xn, which is equal to 0, or the first derivative at x naught is equal to the first derivative at xn, which is equal to 0, or we can specify generally, okay, the first derivative at x naught is equal to any specified value, non-zero, and the first derivative at xn is also any specified value that we require. And in case of fifth order splines, we have 4 conditions, and if they are 4, we can add with ease those 4 conditions regarding the position and regarding the velocity and acceleration. So this is regarding the acceleration at the 2 nodes x naught and xn, and this condition is regarding the velocity at the first derivative at the initial and final node. So I wish that by this clarification everything is clear, and we will go to the examples. Okay, here in the examples, we have in the first example a given data points which are 4. We have 4 data points. Okay, so what are the number of splines? They are less than the number of points by 1, and as a result they are 3. And we want to construct a linear splines. M is equal to 1. So M is equal to 1. So total number of unknown coefficients, they are 6. And total number of position conditions, they are 6. So this means that there is nothing left for the derivative continuity, and there is nothing left, they are zeros, for the additional conditions, and the total number of conditions is 2n. And here we construct the 3 polynomials f1, f2, and f3. They are first order splines, and the first polynomial connect the range of x between 1 and 2, which are those 2 points, and the second between 2 and 5, which are those 2, and the third connect between the last pair 5 and 8. They are all of them first order polynomials. So we take the position conditions for those data points. For each polynomial we have 2 conditions. Okay, so we have fi of xi minus 1 is equal to f of xi, and fi of xi is equal to xi. So we generate 6 conditions with 6 unknowns, and if we solve them, we will generate a system of 6 equations, and the unknowns, they are the a's, and we solve it and we get this a, and finally we substitute them and get those equations, and it's required to find the value of xi, which is equal 4.5, and 4.5 lie within the second order, the second spline. 4.5, x is equal to 4.5, lie within the second spline, and if we substitute it within the second spline, we calculate its value, and these are the figure. This is the first spline, this is the first spline, this is the second, and this is the third, and all of them, they are linear, and this is the node that we are calculating. It lies on the second spline. So let us go to the next example. I think we have the same points. We have the same points, okay, 4 points, and we should increase the order of spline to 2, quadratic, and then we should find the value at x is equal to 4.5. So here the spline order is given as 2, specified, and the number of polynomials, it's less than the number of nodes by 1. So we have 4 nodes, the number of polynomials will be 3, and based on that the total number of unknown quotients, they will be 9, and position conditions will be 6, and derivative conditions will be 2, and additional conditions will be 1. Okay, so these are the 3 polynomials, and each one of them is a second order polynomial, and each one of them cover a range between the first, second, and third and fourth point. And we will start with the position conditions, and based on those position conditions we will generate 6 conditions. They are 3 splines. By 2 conditions from the left and right, we will generate 6 conditions. They are those, and then we switch to the continuity conditions, and those continuity conditions, they will be for the first order derivative only, because here the spline order is of order 2. So m is equal to 2. So m minus 1 will be 1. So we will only calculate the first derivative. Here we are calculating the first derivative for the three polynomials, and we are applying it for the left and right continuity condition for the interior nodes. And we have only two interior nodes. We have here two interior nodes because this first node is edge and this last node is edge. So we have two interior nodes, 2 and 5. And based on that, we calculate the derivative of the three polynomial, the first derivative. And if we continue, we substitute the condition that the first derivative is equal at x1 for the right polynomial and the second, and also the first derivative for x2 is equal for the right and left polynomial, and we add additional condition, which is the first derivative at x0 is equal to 0, and finally we will get 9 equations with 9 unknowns, and these are the unknowns, and this is the matrix coefficient A, and this is the right hand side, and finally we will get those answers, and if we substitute them we will get those three polynomials, and finally we substitute x is equal to 4.5 and we will get this value. And those are the three splines. This is the first spline, this is the second spline, and this is the third spline. Each of them is of second order, and the data point lies within the second spline. So we will continue in the first data points, and in this case we will generate a third order spline, and again we will approximate the function value at 4.5. So the spline order is 3, and still we are speaking about 4 data points, so the number of splines will be 3, and in this case the total number of unknown coefficients will be 12. Among them 6 will be position conditions, 4 will be continuity derivative conditions, and 2 additional conditions will be added. And this is the third order splines, first, second polynomial, third order. Each one of them is third order, and each one of them is covering a range of the data points. And we start with the position conditions, and we generate 6 equations, and after that we generate the continuity condition. But here the continuity condition is not for the first derivative, it's also for the second derivative, because here the order m is equal to 3 and the continuity is till m minus 1. So we means that this continuity will be for the first derivative and the second derivative, and then we apply those continuity conditions for the first and second derivative. We will generate 4 equations, and finally we will add 2 conditions regarding the position, the velocity at the initial and final node, and all of them will be 0. And here we generate a system which is larger, 12 by 12, and this is the system. This is the A coefficient matrix, and this is the right hand side, and this is the unknown matrix. Here it's A, and finally when we solve we get those answers, and we substitute them, and we find the third order splines for each case, and each polynomial is covering a certain range. Okay, and those are the splines. This is the first spline, this is the second, and this is the third. And as I mentioned, the point 4.5 lies within the second spline, and this figure is very important because it shows the original splines along with their derivatives. So if we pay attention, this is the first spline, this is the second, and this is the third spline without any derivative. While this figure, this is the first derivative of the first spline, this is the first derivative of the second, this is the first derivative of the third. And if we pay attention, these are the via points. So there is no discontinuity. The left derivative is equal to the right derivative. This point, the derivative of f1 at this point is equal to the derivative of f2 at this point, and this is continuous derivative. And also for this point, the derivative of this polynomial at this point is equal to the derivative of this polynomial at this point, and it's continuous. There is no discreteness. And here we switch to the second derivative, and also the second derivative is continuous. There is no any jump. While if we pay attention to the third derivative, it contains a jump. Here it's not this continuous. It here, there is a jump here and there is a jump here. So the third derivative is not continuous, while the first and second derivative, as we mentioned in the solution process, they are continuous. So let us continue and take this example, which is the same larger number of data points. Here we have larger number of data points. Okay, we have 6 data points, and we want to construct a spline of order 5. So spline order is order 5, and since the number of data points is 6, this means that the number of polynomials will be 5, and here the total number of unknown coefficients will be 30. Among them will be 10 position conditions, and the derivative continuity conditions will be 16, and the additional conditions of order m-1 will be 4, and in total we have 30 unknowns. So these are the 5 polynomials. Each one of them is of order 5, and each one of them is covering certain range. So for position conditions, there will be 10 conditions. Those 10 conditions, they are regarding the position conditions, and if we continue, we will generate another number of conditions, which is of order number of conditions here for the continuity is equal to 16. So we will generate 16 conditions from the continuity on derivative conditions here. Okay, we will apply this condition for the derivatives from the first till the fourth derivative, since the order of the polynomial is 5th, and we will generate it on all of the via points. We have six points. 4 of them are via points or intermediate points, and the derivative order from the first till the fourth. So this means that 4 by 4 there will be 16 conditions. So this is the derivative, first derivative, second derivative, third derivative, and fourth derivative of the splines, and then we apply it at each node for the first via point, the second via point, the third via point, and the fourth via point, and each point will result in 4 equations. So 4 by 4 will be 16, and we will add additional conditions of okay, the additional conditions, if we go back to the table, it should be, since the order of the polynomial is 5, we will have 4 additional conditions. Here we have 4 additional conditions. Since the polynomial order is of order 5, m is equal to 5, additional conditions will be m-1, which is equal to 4. So additional conditions will be 4 additional conditions regarding the first derivative and the second derivative at the initial and final. So here, the first derivative at the initial is equal to 0, the second derivative at the initial is equal to 0, and the first derivative at the final point is equal to 0, and the second derivative at the final point is equal to 0. So we have 30 equations with 30 unknown, and this huge matrix is generated. And if we solve this huge matrix, we will get those unknown coefficients, 30 unknown coefficients, and finally we will construct the 5 polynomials, each of order 5, okay, and if we draw them, these are the original polynomials without any derivative. This is the first order derivative, second, third, and fourth, and as we mentioned, since it's 5th order, there will be continuity of the derivative at the via points until the 4th derivative. So this is obvious that this is continuous at the via points. This is continuous till the 4th, while the 5th derivative is not continuous, as we are observing here. It's not continuous. There is a jump in the values. Of the derivative in the 5th order derivative. Here there is jump here, small jump, and this is what we mean by the continuity of the derivatives. And in this way we have completed this chapter, and the interpolation and the splines is over. And in the next chapter we will cover the numerical integration and the numerical differentiation. Wish you a very nice time, and wish you that understand everything in this lecture. Thank you, and bye bye.